Okay, so we can start now. Let the student join and they can watch. Or maybe they can watch the recording also. So next topic is cache organization. So in the cache organization, first of all, what is cache memory? So what is cache memory? Cache memory is a small very fast memory which is placed between CPU cache memory and RAM. So between CPU and RAM, so between the CPU, okay. So we do what we do here between the CPU and the cache, okay, we place the cache. And why it is useful? So its job is to store the frequently. See the word frequently. Its job is to store frequently used data or instruction so that CPU can access them quickly. Okay, so that CPU can access them quickly. Now, what is the concept? Like why the cache is working? Okay, like why the cache is working. So for that, we have two types, which is spatial locality and temporal locality. So what is temporal locality? So particular address access again and again, right? Particular address access again and again. So see, why the cache will work? Cache will work because of the locality, right? Because of the locality. And there are two types. So first is spatial and temporal. First is spatial and temporal. So what the temporal is saying, so particular address will access again and again. So if particular address, if this address will access again and again, so why don't we store it in a cache, right? Why don't we store it in a small memory, and which is very fast, so that we don't have to go to the RAM every time. We don't have to go to the RAM because this address will be accessed again and again. So what we do, this content we will store in the cache, right? We will store in the cache. So that is the temporal locality. Now, what is the spatial locality? We have one another type. So what is the spatial locality? Nearby address will likely to access, right? Nearby address is likely to access. So it's like if you want if you are doing array access, right? Array access. If you are doing array access, like if you are accessing A0, then A1, right? Then A2, and so on, and so on. So here you access the address is nearby, right? So like nearby address, see, then first A0, then A1, then A2. So particular nearby addresses, you access them again and again. So for that, we are doing speculation, right? We are predicting. It's like we are predicting that in the future, maybe this address can be accessed. In the future, maybe this address can be accessed. In the future, maybe this address can be accessed, and so on. So we are predicting that maybe we can access. So that's why, if we are predicting, why don't we put everything into the cache, right? Why don't we put everything into the cache? So it is based on the block size, basically block size, that in a block how many elements you can put. Okay, so that is your spatial locality, right? That is your spatial locality. So it says that nearby address will likely to access, right? Likely means in future, in future. Okay, likely means in future. So now in a cache, uh, this is all about its introduction, that why the cache is needed, what is the concept behind it, right? Now the majority of gate pyqs comes from this particular topic, right? This particular topic. So now we have three types of mapping. First is direct, set associative, and fully associative. So there are three types. Now now why the mapping is needed, right? Why the mapping is needed? So see, here, if this is your CPU, right? If this is your cache, and if this is your main memory, right? This is the main memory. Now you know that main memory have blocks, right? If this is the block 0, then block 1, block 2, and so on, right? And so on. Here in the cache also, in the cache, because cache is also memory, right? So here also it have the block, right? It have the block. Now, what is the mapping? What is the mapping says? So why that topic is required? So because see, because the main memory, from the main memory, blocks will come into the cache, right? Block will come into the cache. So we there should be some mechanism, right? There should be some mechanism in a way that this block can be mapped to out of this four block, right? This b0 block will map to anyone, like which one, right? Like out of this four block, out of this four block, b0 will maps to where? Maps where? It asks the question where, right? Then b1 also asks the same question, that I will map to where, so maps where, right? They will map like they don't know that where to map, right? They don't know where they have to map it, where they have to map. Like b2 doesn't know that where it have to map. Now 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 who give this answer, who give this where answer? It is given by three types, right? You have three types of mapping. So direct mapping, then set associative, and fully associative, right? So each method will say that where this block have to map, right? Where this block have to map out of these four blocks, right? Out of these four blocks. So because of this we require that particular concept, right? We require three types of mapping: direct mapping, set associative mapping, and fully associative mapping. So now we will see each one. Now we will see each one. So see, cache memory is not addressable, it's indexable. So indexable means cache memory have indexes, right? Cache memory have indexes. Cache memory have indexes. Now, now see the next point. Block size of cache and main memory are same, right? So if you have learned COA, you would know that this block size, and here any block size, right? So block size of cache is same as block of block size of main memory. Yes. So the block size is same to same, right? Same to same. Now, next point, CPU always generates the main memory address by default, right? CPU always generates the main memory address, because CPU doesn't know that there is a system, right? So if this is the CPU, here if you place the cache, CPU is unaware about the cache. CPU is unaware that there is something called as cache which is present in the system, because CPU every time it always generates the main memory address, right? It always generates the main memory address, because of the system architecture have designed the system in that way that CPU doesn't know that you are going to the cache and stuff like that, right? We will see this. I have already put the points in the further, right? So we will see this point. Okay. Now, see, next point is line, block, or index. If someone would say line, it is also called, it's same as block. Okay, it's same as index. So it have different meanings. It have different meanings, right? All are the same. All are same. Now, how to find number of blocks in the cache memory? How to find number of blocks in the cache memory? So if you have, for example, if you have size of cache, right? If you have size of cache and block size, you can just divide it. You can just divide it, right? Because one block, see, if you have block size, so assume that example, let's say your cache have 32 KB, right? 32 KB, and your block size is 16 byte. So how you find? So if you don't know this formula also, still you can do normal mathematics, right? Because one block will have 16 bytes. So if you have 32 KB, then how many blocks, right? This is simple pure maths, pure maths. So 32 KB divided by 16, right? So 16 2, so 2 KB, right? So 2K blocks, 2K blocks. Yes or no? 2K blocks. So the same thing it is written in the formula. If you in the exam also, if you forget the formula, you can do with the simple method. That's why the understanding of concept is very required. Right? Understanding of concept is very much required. Now see, now the next point. Okay, now talking about the next point. If the main memory address is given, okay, main memory address is given in decimal, right? In decimal. Then what is the block number? Tell me, what is the block number? So he if main memory address is given, right? If main memory address is given, then what is the main memory block number? What is the main memory block number? So if you have this, right? So for example, right, so for example, if you have this block, right, if you have this block, now each block contains, so uh, okay, maybe I can. Okay, if this is the B0 block, if this is the B1 block, right? So each block have some size, right? Some size. So each block have some bytes, like one block equal to, for example, one block equal to 1 2 3 4. So 4 bytes, right? 4 bytes. So one block here 4 bytes. So every byte have address, yes or no? Every byte have address. So here this is whatever address, right? Whatever main memory address, assume that 01, then 02, 03, 04, 05, and so on, right? So this is the particular address of the byte, yes or no? This is the particular address of the byte. Now you want this entire block number, right? This entire block number, like what is the block number for this? What is the block number for this? Because CPU will generate this byte address, right? CPU generates byte address, right? So now you want block number, yes or no? You want block number. So what you can do, simple math, right? Simple math. See, same thing. If one block, uh, yeah, you can. Yeah, so for example, one block have, let's say, 16 byte, right? 16 byte. Now, if you have some address, right? Because if you have some address, what you can do, you can just divide by 16, right? So see here, the formula also you can see, like address divided by block size, and you have to take floor of it, right? You have to take floor of it, divide by block size. Yes, got it. So this way you can find if main memory. So please see in the question, right? Please see in the question that what it is given in the question. See this very carefully, because student will make mistake in here only. If main memory address is asked or main memory block number is asked. Okay, please see in the question. Please see in the question. Right. So now I have wrote some of the formulas here which are important. So cache memory block number. How you can find the cache memory block number? How you can find the cache memory block number? So first you have to find main memory block number, right? Main memory block number modulo number of blocks in the cache memory, right? Number of blocks in the cache memory. So this mapping is for diag, right? Diag mapping. Diag mapping uses this, like it is a mapping technique. Yes, diag mapping is a mapping technique. Diag mapping is a mapping technique. So what this mapping technique will say, what the mapping technique will say, first of all, you should have your main memory block number, right? You should have main memory block number. Then you just have to do modulo with total number of blocks in the cache memory, right? Total number of blocks in the cache memory. Now, how you can find, okay, now next point, how you can find cache memory set number. So same thing. You first required main memory block number. Modulo, you take it with number of sets in the cache memory, right? Number of sets in the cache memory. So this technique is used in set associative mapping, right? Set associative mapping. Now, next point is, if someone can ask, okay, if someone can ask number of sets in the cache memory. number of sets in the cache memory. Then how you can find? You can find with simple way, right? So number of blocks divided by associativity. Okay, divided by associativity. So for example, if you have given, okay, example, you would have given two-way associative. Okay, two-way associative. So what does it mean? What does it mean? One set will have two lines, right? Two blocks or two lines, whatever, right? One set will have two blocks or two line. Yes. Now you want to find total number of sets in the cache memory. So if you have total number of blocks, right? Number of blocks in the cache you have, you can easily find number of sets. Yes or no? You can easily find total number of sets. Yes or no? So same thing which is written here, number of sets in the cache memory is same as number of blocks divided by associativity, right? Divided by associativity. And next point, tag bit is maintained for each block in the cache, right? Tag bits is maintained for each block. Like if you have, if you, so if this is the cache, right? If this is the cache, if these are the blocks, if these are the blocks, tag is maintained for each block. Okay, tag is maintained for each block. So these are the tag, right? These are the tag. Now talking about each method. Okay, now we will see each method in somewhat detail. Okay, somewhat detail we will see each method. So what is the diag associative? Diag associative you can also say as one-way associative. Okay, one-way set associative, right? So one-way set associative means one set will have one line, right? One set will have one line. Okay, one set will have one line. Now see this. Now see the points. Okay, each main memory block maps to exactly one line, right? Exactly one cache line. Each main memory blocks maps to exactly one cache line. Now, how it maps? How it maps with the with this formula, right? With this formula, with this formula, with this formula, each main memory blocks will map to cache line. Yes or no? Because that is only written here in the diag mapping. You can find the cache memory block number with taking the modulo, right? We're taking the modulo. Now, if two blocks, okay, the next point. So next point is if two blocks want the same line, right? If two blocks want the same line, then what will happen? What will happen? Then will that will be the conflict miss? Yes, that will be the conflict miss because two blocks want the same thing, right? Then it will be the miss. Then it will be the conflict miss. Now, cache controller stores cache controller stores tag. So what the cache controller will store, it will store tag directory size, right? Tag directory size, like for all the mapping, right? For all the mapping. And what is the tag directory? What is the tag directory? Number of blocks in the cache, yes, into tag plus extra bits, yes. So whoever has done the COA, they might know that other than tag, these are there are some other bits, right? Like valid bit, then dirty bit, yes, dirty bit. All the extra bits will store, and that is stored for each block, right? That is stored for each block. So tag directory size will be number of blocks in the cache, right? Total number of blocks into tag plus extra bits, right? Tag plus extra bits. So this is the size which tag directive will store. Okay, this is the tag directive size. Now next important point of diag mapping is that there is no replacement policy. Okay, see, no any replacement policy required. Okay, no replacement policy required for diag mapping, as it is automatically replaced because it have fixed location, right? They have fixed location. So see here why the replacement policy is not needed. So if see, because the mapping is fixed, right? Because the mapping is fixed. See, each main memory blocks, they maps to exactly one line, right? Exactly one line. So they knows that they have to map like here. They have to map. So for example, if this is the diag mapping, right? So see, So if in for assume that two blocks have come, right? B0 block. So B0 block is present already here. Okay, B0 block is already present here. Now let's say B1 block comes. Let's say B1 block comes. Okay. Uh, okay, maybe. Okay. Let's say it's one B0, 1, 2, 3. Let's say B4 block comes. Okay, B4 block comes. Now you know that B4 will map to where? B4 will map to where? Because it is index 0, 1, 2, and 3, right? So where the B4 block is mapped, so we know that what we have to do, 4 mod, total number of blocks, right? Total number of blocks is 4. So it maps to 0, right? It maps to 0 because it has fixed location, right? It has fixed location. See, what I have did, I have just did I will just use this formula, right, to find the cache memory block, like main memory block number, modulo I took with total number of blocks, yes or no. So I got that, I got to know that it will map to 0. It will map to 0. Now, we know that B0 is already present. We know that B0 will already present. So what will happen? What will happen? It will automatically replace, right? It will automatically replace. So that's why they have told no policy is required, right? No policy. So no algorithm is used. Policy means replacement algorithm, like you know, right? That FIFO is there, LRU is there. Everything is not required here. Everything is not required here. It is automatically replaced, and B1 will come here. Okay. Oh, sorry. B4 will come here. Right? B4 will come here because those locations are fixed. Right? Those locations are fixed. Got it? Yes or no? Got it? This thing. So now next point, how to find the tag, right? So maybe you can use it can be cleared with by this mapping formula. So tag will be main memory address minus log of cache memory size. Okay, minus log of cache memory size. So we'll see in a couple of minutes. Okay, we'll see in a couple of minutes. So what is tag? It identifies among the competitor, right? Among the competitors. So example, okay, what the tag will identify among the competitors. So see here, for example, for B2, okay, here let's say B2 is there, okay, then B4, B5, let's say B6 is there, okay, then let's say +4, then B10 is there, right? So let's say many competitors are there, right? Many competitors are mapping, like many competitors have is presented. Now we wants to know that, and you know that all this, right, 2, 6, 10, all these blocks maps to 2, right, maps to 2. Now you know that you want to know that which block will present here out of the competitors, right? Out of these competitors, you have to see that which block will present, whether B2 is present, whether B6 is present, whether B10 is present, which one. You have this question that which block which block is present. How I can know? You can get to know with the help of tag. Okay, you can get to know with the help of tag. So here tag is used for each block, right? Tag is used for each block. So with the help of this tag, you can get to know that which block will present here. Okay, which block will present here. Got it? Yes. Now, what is the line number and index is? What is the line number and index? So it tells which cache line to check. Okay, it tells which cache line, because this is the line number, right? This is the line number. So line number will tell that which cache line to check. Okay, which cache line to check. And now what is the block offset? What is the block offset? It tells which byte or word within the block is needed, right? Within the block is needed. So see, if you have this block, right? If you have this one block, right? This is the block, right? And here you have many bytes, right? In each block you have many bytes, many bytes. So what is the byte offset will tell? Byte offset means how much offset you have to go, right? Like which byte you required, which byte you required. So for example, if this is the byte you required, so this is your offset. Okay, this is your offset. Got it? So it tells that which byte or word inside the block is needed. Okay, inside the block is needed. Now So till now everything is fine. Everything is clear. Just give me fast. Tell me fast. Okay, so now we will see the mapping formula, right? See the mapping formula in case of diag mapping, right? In case of diag mapping. So diag mapping. So here, this is the main memory address, right? This is the main memory address. This is the main memory address. Now, what we done, we break the main memory address into different parts, right? Into different parts, we have divided the main memory address. So see, first what we did, we divide the main memory address by byte offset, right? By byte offset. So what you get. So look into this formula. Look into this formula. If main memory address is given, if you divide by block size, right? If you divide by block size, what you will get main memory block number. Yes. So if you divide here, okay, if you divide here, all this thing will be your main memory block number. Okay. This is the main memory block number, right? Now, look carefully. Now, if you have main memory block number, yes, if you have main memory block number, now tell me, you have main memory block number. How to find cache memory block number? I have already told what you have to do. Total number of blocks in the cache memory, you have to take mod, right? You have to take mod. So see here, you from the main memory block number, and you know that modulo will give the lsb bits, right? Modulo always gives the lsb bits. So if you do modulo, it will again divide into two parts, like tag and cache memory block number. Yes. Cache and tag and cache memory block number. Yes or no? Now, now see how to find the byte offset. So if your block size is 32 bytes, so here you have to write in terms of bits, right? So so byte offset will be 5 bits, right? 5 bits. Now here, if you total number of blocks, for example, let's say 128, then this will be 7, right? This will be 7. Cache memory total number of blocks will be 7, right? So this way you have to find out, right? This way you have to find out. Now one important thing, okay? One important thing you can figure out again. So see, here you know that this is the block size, right? This is the block size, right? This is the block size. Now block size of cache and block is the same. So here you will get total number of blocks in cache memory, right? In cache memory. Here you will get block size. Then what it will be? It will be the cache size. Yes or no? This will be the cache size. Cache size will be total number of blocks in the cache memory into block size. Yes? Yeah, total cache size. So see this. Uh, See this part. Okay. Maybe I can erase this all unnecessary. Okay. So look here. This will be from starting with here to till here. It will be your cache size, right? It will be your cache size. It will be your cache size. Yes, cache size. Because this term will give me total number of blocks in the cache memory. Total number of blocks into block size. If I multiply, right, this term will give me block size. Then I will easily find cache size. Yes, I will easily find total cache size. So this way you can find small things, right? This way you can find small things. Now this is the entire diag mapping, right? This is the entire diag mapping. Now see some advantage and disadvantage. We will see advantages. What is the advantage? It is simple and fast, right? It is simple and fast. So it's simple and fast. It is the cheap hardware, right? It requires cheap hardware and easy to implement. Why? Because the mapping is very simple, right? Mapping is why each thing is simple and fast, right? Because the mapping is very simple. This mapping, right? This mapping, it maps to exactly one cache line. This is very simple, right? This is very simple. You just have to do mod, right? You just have to do mod. But what is the disadvantage? What is the disadvantage? High conflict miss, right? High conflict miss. So high conflict miss, right? High conflict miss, because many blocks if come, right, many blocks if come for one location, right, for one location, let's say b0 comes, then let's come, then let's say b8 come, and then b12 come, and so on. But you have one location only, right, you have one location only, so many conflict misses, right, many conflict misses, many conflict misses. Yes, got it. So this is all about your diag mapping. Okay. Now we will see another mapping. Now we will see the next mapping. Now we'll see the next mapping. So associative, right? Set associative. So set associative, your entire cache is divided into sets, right? Entire cache into sets. Set has k lines, right? Each set has k lines. What is the index in set associative? So set number, right? Means index means this is also called as index, right? This index. So here, they are saying that what is the index in the set associative mapping? What is the index? It will be the set number, right? We are writing the set numbers. Now, what is the mapping? What is the mapping? So see here, look here, look here. What is the map? This is the mapping formula. This is the mapping formula. How to find the set number? So block number, you do mod with the total number of sets. Yeah, no, you do mod with the total number of sets because it is the total number of sets, and then you can get the set number. Yes, for main block. Okay. So if this is your one set, right? If this is the set 0, okay. So see here. If you look here, if this is the cache, right? If this is the cache, okay, got it. Now let's say, okay, let's say this is the B0 block, then B1, then B2, and B3. Okay, and let's say two-way associative. Okay, two-way associative. Now, what is two-way? Which means one set. Okay, each set has k lines, right? So each set have two lines, right? Two lines. So if you have four lines, how many total number of sets are present? How many total sets are. So two sets, yes, because one set, if you have four, how many sets? How many sets? So it will be four divided by two, four divided by two. So we divide into set zero and set one. Yes or no? We divide into two sets, set zero and S0 and S1. Yes. Now what is the mapping formula? Mapping formula says that you have to just do with mod. You have to take mod with the total number of sets. Okay. Assume that. Now assume that B. Okay. Maybe I can erase this thing. Okay, this is just for your understanding that four blocks are present. Okay, four blocks are present. Yes. Yeah, this is just for your understanding that four blocks are present. Let's say now B0 come and B2 come. Then where the B0 will map, what you have to do? You have to do mod with the total number of sets. So total number of sets are two, right? So you have to take a mod. So 0 mod 2 will be 0. So B0 will map here. So here a block can go to any line within the one set, right? So it is not necessary that in inside S0 it can map here, right? It can go to anywhere. It can go to anywhere inside one set. Okay, inside one set it can go to anywhere. Okay, inside one set it can go to anywhere. Now let's say B2 comes. Okay, so 2 mod 2 will be 0, right? So set 0 it will be mapped. It will be mapped to set 0. So B2. Yes. So this is how it will map. This is how it will map. Yes. Now, okay, so now this thing, if associativity is double, set number reduced by one. So we'll see this point in couple of minutes. Okay, so hold on this point. We will see this. Now, how to find the tag? How to find the tag? So here, the same thing, right? Tag will be main memory address minus log of cache size minus log 2 of k. Okay, so see, first of all, you can easily find it. So tag you can just do like if this is the main memory address, right? If this is the main memory address, what you can do, main memory address minus set offset minus byte offset, right? But this is one another formula. This is another formula. It can be useful only when cache memory size is given. Okay, no information about block size is given. Only when cache memory size is given, right? So so we'll see this point also. Okay, when we discuss this point, we can also see this point. Okay, so both the points, just hold on for a couple of minutes. Okay, and here number of comparator will be key required. So I think this is not very much important. Like this should be not included in the short notes, because till now only one gate question have been asked for the hardware, right? For the hardware side. So like what is the hardware? Because that particular line is for hardware. Like in a how the yeah, how it had been implemented. Okay, so till now, like only one gate PYQ have come, and that too also in, I think, gate 2008 or 2010. I don't remember the, or 2013. I think I don't remember the exact gate year, but it is not required in the short notes. Right? It is not required in the short notes. Like when you do the course, in that, when you do the entire course in that, I think your instructor have told you, but it not required in the short notes. Now this is called KWA set associative. Yeah, so this for the general KWA associative, right? KWA set associative. This way, this is the mapping, right? So tag, then instead of in line number, right? In the, here, see here you have block number, right? Here you have block number, but here you have to give set number, right? Or set offset, set number or set offset, right? Set number or set offset. And this field is same, right? Byte offset, this field is same. Okay, now see one important property you can say, or one important concept you can say. See this is important. Now see, look here. If you see, if this is the index, right? So this used for tag comparison, the tag is used. Now this is the set and this is the offset. So what happens here? If you increase the associativity, right? See, if you go this side, okay, if you go this side, then what will happen? If you increase this side means increasing associativity. Okay, like going to the right side. Okay, going to the right side, which means this bit, okay, this bit will shifted here. Okay, this bit will shifted here, which means that tag will increase, right? Tag will increase, yes or no? Because if this bit will shifted here, okay, then the total number of bits in the tag will increase. So increase, okay, so tag bit will increase if you increase the associativity. Okay, if you increase the associativity, like what happens, okay, see what happens. This is the very much concept. Okay, so example, you have two-way associative, right? Two-way associative. And then if you have four-way associative, okay, four-way associative. Okay, so now what happens? Assume that blocks, okay, total number of blocks, you have total number of blocks, let's say, assume that 256. Okay, assume that 256. So how many total number of blocks in two-way? 128, right? 256 divided by 2, right? 256 divided by 2. What is the four-way? 256 divided by 4. Can someone tell the answer? 256 divided by 4, what is? I think it is 60. 64, yes, 64. So see this. See here, 128 sets, right? Total 128 sets. So how many bits? How many bits? 7 bits. Yes or no? 7 bits. Yes or no? If you have 64, then how many bits? 6 bits. Yes or no? 6 bits. Now, let's say eight-way, right? Assume that eight-way associative. Now, how many bits? How many bits? Just one bit, right? 256 divided by 8. So what it will be? 32, right? 32. So 5 bits, right? So see clear. If you increase the associativity, you have increased, right? You have increased the associativity, right? See here, two-way, then four-way, then eight-way. So you increase the associativity. what will happen? This index bit decreased, right? See, index bit keep on decreasing. Index bit keep on decreasing. So similarly, tag bit will increase. Yes or no? Tag bit will increase. If if this index bit will decrease, then someone have to increase it to maintain the equilibrium. To maintain the equilibrium, one thing if it is decreased, then other have to increase to maintain the equilibrium. Yes or no? So see here, if index bit will decrease, then tag bit will increase, right? So this is one important concept. So that is the concept, and that's what here written. If associativity is doubled, right? If associativity is doubled, so from two-way to four-way, right? From two-way to four-way, if you go example, right? Example, what happens? Set number just reduces by one, okay, and tag increases by one, right? So we have seen here, if we have doubled the associativity, right? From four-way, for example, see here. Okay, look here. From four-way to eight-way, we have gone. Then what happened? Just a one bit change, right? Just one bit change. So one bit have to ions. So who will increase? Tag bit have to increase, right? Tag bits increased by one. Yes or no? Is this clear? Because address will be generated of same bits by CPU. Yeah, yes. Okay. So this is the concept, right? This is the concept. Now see this. Now I have told you I will discuss this point. So tag will be main memory address, right? Main memory address minus log cache size minus log k. So what it says? So here look here, as in the diag mapping we have seen, right? In the diag mapping, what we have seen, this portion will be your, okay. Maybe I can use another color. I hope I hope this, okay. It's not visible. Which color? Yeah. So maybe you know that from here to here, your that will be your cache size, right? That will be your cache size. So here tag will be main memory address minus cache minus log of cache size. Yes or no? Yes or no? Here in the diag mapping, yes, in the diag mapping. But see here, look here. Here in the set associative, what into cache is divided into sets? Yes or no? Cache is divided into sets. So what will happen? What will happen? Based on the associative, right? Based on this associative, these bits, right? These bits will shifted. Yes or no? This bit will shifted. So this tag bit will increase. So these bits also will decrease, right? These bits will also decrease, which is earlier used for cache size. Yes or no? Earlier these bits, okay, assume that this earlier, see, earlier this bits is used for cache size, right? Earlier this for cache. Now because of, okay, so see, this is the earlier scenario. Now if this is the size, because of associative, these bits are decreased, right? These bits are shifted, so that tag is increased, right, from two-way to four-way. So that is the thing here. Main memory address minus what you have to do, log of cache size minus log k, right? Minus log k, minus log k. Okay, you have to just do minus log k, minus log k. Okay. So high level idea also I have gone in little bit detail, okay, but I think this is only required for the short notes, okay. uh, because in detail I have discussed in the lectures, right? In detail I have discussed in the lectures, but here I have told you to at least you got the idea, right? At least you got the idea why we are, how this formula have, how this formula came. Yes. So so now we can proceed further. Replacement policies are used, right? So it is required within the set, right? Because we have seen earlier that within the set, see here it's already written, a block can go. Assume that now here, okay. So assume that, for example, here if B0 present and B2 present, okay, and you have two sets S0 and S1, okay, and four blocks. Now assume that B4 come. How it where it will map? B4 will map to, so 4 mod 2, what you have to do? 4 mod 2, right? So it will be 0. 4 mod 2 will be 0. Yes. So B4 block will map to S0 set, S0 set, yes, S0 set. Now you have two locations, right? Two locations. Like which to replace, right? Now which to replace? Which to replace? So for that, you have a replacement policies, right? You have a replacement policies. So these are the algorithms, and mainly see these two is very very important, right? Very very important. And every I think none of the PYQs other than these two policies have come. Okay, so these two have very much important, very very important. In a gate, if you look into gate PYQs, only from LIU and FIFO the questions have come. Okay, and see if they want to invent their own policy, right? Assume that in a gate 2027 one new policy have been introduced. Okay, so each and every necessary details they will mention. Each and every necessary details they will mention in the question, so you don't have to worry. Okay, if some new policy have introduced by gate professor, they will definitely mention. Now now FIFO and LIU. Okay, so LIU is most common and FIFO. So yeah, maybe I have written here. So what the FIFO will say: first in, first out. So check which block came first and replace them, right? You have to just check which block will came first and you have to replace that. Now FIFO is pretty much simple, right? First in, come first out. So if you have came first, you have to go first. Okay. Now next is LIU. LIU stands for least recently used, right? Least recently used. What the definition says: replace the block which has not used for longest time, right? You have to replace that block which is not used for longest time, right? Which is not used for longest time. So here assume here example. Okay, maybe I can give example. Okay, so here assume that B0 have come, then B2 come, then let's say B4 came. Okay, then let's say B4 came. Now tell me which block to replace. So here B4 have two opportunities, right? For LIU which to replace. So what is the definition says? You have to replace the block which is not used for longest time. Tell me which to replace. So you have to, what you have to do, I have told you, you have to look backwards, right? You have to look the request, right? The sequence, right? The sequence you have to see backwards, and you have to see, this is recently used, right? This is recently used. This is not used for the longest time. Okay, this is not used for the longest time. So B0 needs to replace, right? B0 needs to replace. So this is the LIU policy, right? This is all about your LIU policy. This is all about your LIU policy. Now, what advantage? So, fewer conflict means that, right? We've seen that we conflict have handled here because that, right, in a one set, many locations, right? Many locations it can go. It can go to many locations. So here fewer conflict means, but what is the disadvantage? Slightly more hardware, right? You have to do many comparisons, you have to do many tag comparisons and all, like complex hardware. Okay, complex hardware, right? So slightly more hardware. Now, so till now everything is clear. We have seen two mapping, diag mapping and set associative. Now we will see the last mapping, which is fully associative. Now we will see fully associative. So now see this, it is the most flexible mapping. A main memory block can go to any cache line, right? There is no mapping, right? There is no fixed mapping, right? There is no fixed mapping. Like it can go to anywhere, right? It can go to any cache line. It can go to any cache line, no fixed position, right? No fixed position. Now, next point is, so comparator will be total number of lines, right? If you want to compare. So if you have assumed that this is the cache, right? This is the cache. Okay, this is the cache. And you have one, two, three, four, five blocks, right? Five blocks. Now if a new request have come, you have to see, right? If a new request have to come, you have to see that where this will map. Like If you have to see, then you, because a block can go to anywhere, right? A main memory can go to any line. Then you have to compare with this, you have to compare with this. So total number of comparators will be, comparators means comparison circuit, right? Comparison circuit, comparison circuit. I think the hardware part is not that much important. Okay, you can skip that point also. Okay, you can skip this point also. So comparison circuit will be required, will be total number of lines. So that one, that's what only required. Right? Total number of comparators will be total number of cache lines, right? Because you have to compare this with this, right? Now in a fully set associative, tag will be your main memory block number, right? So yeah, see, okay. Okay, so we'll discuss this point. We'll discuss this point. But here, uh, okay, so we can directly first see and then we'll see these 3 points. So what is the mapping formula? Any block can go to any line, right? Any block can go to any line. So this is the mapping formula. So here, if this is the main memory address, right? Main memory address. Okay, okay, main memory address. So what it will be? Okay, so here there is only tag and byte offset, right? There is tag and byte offset. So this is the main memory block, right? Main memory block, because the address you divided with, divided by block size. Okay, so this formula I have already wrote here. See, the same thing. I have not done any other thing. If you have main memory address, how to find the main memory block number? Divided by block size, right? Divided by block size. So that's the thing, right? That's the thing. So I just divided by block size, right? So this is the block offset or block size, right? Block size. So I have divided. So what I will get? Main memory block, right? So that's what here written. In fully associative, tag will be, tag is same as main memory block number. Okay, tag is same as main memory block number. Now, size of tag. What is the size of tag? So size of tag is maximum in fully and minimum in direct associative, right? Yes or no? Maximum in fully, because here there is no any middle thing, right? There is no any middle thing. So right, and you don't have to divide this main memory block into two parts, right? As we have seen in the diag mapping and set associative, right? We have divided this main memory block into parts, right? This is the index, right? This is the index and tag. But now we don't have to divide, right? We don't have to divide here. So that's the thing. So here, tag will be maximum in fully and minimum in diag mapping, right? Minimum in diag mapping, right? Minimum in diag mapping. Now, why the minimum in diag mapping? Why minimum? Can someone tell why minimum in diag mapping? If you have listened this concept very clearly, you can easily know, because we have discussed here in the set associative, right? In the set associative, based on this k value, based on this k associative, these bits will shifted. So tag will increase, right? Tag will increase, tag will increase. So that's why in the set associative also, it is not, it is not minimum, but it is minimum in diag, right? It is minimum in diag. Now, what is the size of index? What is the size of index? So size of index is maximum in diag and minimum in fully, right? Why minimum in fully? So in fully it is zero. It is zero, right? But why it is maximum in diag? Because you don't have to shift your bits, right? The same concept. You don't have to shift your bits, right? If you don't have to, see here, you don't have to shift your bits. Yes, yes or no? Yes or no? So that's why the size of index is maximum in diag and minimum in fully associative. Got it? Yeah, yeah, yes, yes. Now proceeding further. What is the advantage? It is least conflict issue, conflict misses, right? Because it can go to anywhere. It can go to anywhere. What is the another advantage? Best hit ratio you can get, right? Hit, best hit. Now, what is the disadvantage? Costly hardware and slow tech comparison, right? Slow tech comparison and costly hardware. Why costly hardware? Because you have to compare with everyone, right? You have to compare with everyone. Yes, you have to compare with everyone. So it just the advantage and disadvantage. It's pretty much straightforward. Okay, it's pretty much straightforward. Now, so till now everything is fine. Yes or no? Do you got completely each and everything about three mappings: direct associative, fully associative, and set associative? Yes. Okay. Okay. Yeah. Yeah. Okay. So now we will see three type of meshes. Okay. We will see three type of meshes. Uh, yeah. We will see three type of meshes. Okay. Compulsory mesh, conflict mesh, and capacity mesh. Okay. Compulsory mesh, conflict mesh, and capacity mesh. So compulsory means it is first time means. Okay, first time means is your compulsory means. Okay, conflict means. So compulsory means it's also called as cold means. Okay, cold means. Another name is cold means. Now, what is the conflict means? It means happens because of conflict. Okay, the name itself says conflict because of conflict. And what is the capacity means? Means because of capacity, right? Means happens because of capacity. Now now what are the things we should do? Okay, what are the things we should do to reduce the miss? Okay, to reduce the miss. So to reduce the conflict misses, okay, so see, to reduce the conflict misses, okay, conflict. So conflict means happens because of conflict. What you can do? You increase the associativity, right? You increase the associativity. So for example, before assume that your set have four lines, right? Set have four lines. You increase to eight lines, right? You increase to eight lines, or you increase to 32 lines, or you increase to 16 lines, right? So if you do this, what can happen? You don't have many much conflict, right? You don't have so many conflict. So it will helps to reduce, right? It will helps to reduce because if you increase the associative, what can happen? One set will contain so many lines, right? One set will contain so many lines. Yes or no? One set will contain so many lines if you increase the associative. So if you increase it, it will reduce the conflict means. Okay, what can you do now? Okay, now next point, what you can do to reduce the cold means or compulsory means? You can increase the block size. Okay, block size you can increase the block size. Okay, so previously example, let's say your block contains 16 bytes, right? You can increase to 32 bytes. Why? Because here only 16 bytes of information is stored, but here 32 bytes, right? 32 bytes of information is stored. So it's like if you increase the block size, somewhat your cold miss will increase, right? Your first time miss will increase. Got it? Yes or no? Got it? Got it. There is one question. We can't reduce the cold miss now, sir. Yeah, see, you can by increasing the block size, right? By increasing the block size. Yeah, see, there is thing. So for example, let's say previously in case of 16 bytes, right? In case of 16 bytes, let's say you have let's say first one block will have, assume that 8 bytes, right? And if you do this, total number of blocks, okay, total number of blocks will be, assume that 64. Okay, assume that 64. Got it? So 64 cold miss. Got it or not? 64 cold miss, because those are the first time misses. Okay, so 64 compulsory miss you will get. But now if you increase, okay, now if you increase, so assume that one block will be 16 bytes. Okay. So now tell me, how many total number of blocks now in this case? It will be 32. Yes or no? It will be 32. I have just divided by 2, right? Got it or not? 32. So now if you see here, 32 misses only you will get. 32 first time miss only you will get. Yes, 32 first. So in this way, it reduce the cold miss, right? In this way, it reduce the cold miss. Got it now? Now, yes or no? Got it? Yes? Okay. So now, what to do to reduce the capacity miss? To reduce the capacity miss, what to do? Increase the cache size, right? Because capacity miss happens because of capacity. So increase the cache size, right? Pretty much straightforward. Pretty much straightforward. Okay. Now we will look into some different types of bits. So what the valid bit will say? So I told that other than tag, right? Other than tag, those are the extra bits, right? These are the extra bits. Like other than tag, extra bits are stored, right? For each block. For each block, extra bits are stored. So these are those extra bits. What is the valid bit? If the block is valid or not, right? If the block is valid or not. So initially all the blocks initially, if you open your computer, right? If you open your computer or laptop, okay, initially your cache will be invalidated. All the blocks in the cache will be invalid. But but uh, but then when you request something, assume that you request youtube, okay, youtube.com, then what will happen? youtube.com will be one particular code only, right? One particular code only. So that will be present in your IAM. That will be present in your IAM, right? And then what happens? When you go to some IIT and NIT, you will see that you can do the speculation. What is the speculation? Speculation means you can predict the future. You can predict that now on the next request, maybe I can request something, okay. So you can predict the access pattern, okay. You can predict the access pattern, and based on that pattern you can bring those things into the cache, okay. You can bring these things into the cache, right? And that's why the cache works. Got it or not? That's why the cache works. And then slowly your blocks will be changed from invalid to valid, right? Invalid to valid. Did you got this explanation what I have told just now? Yes? Okay. Now there are some extra bits, which is another bit is dirty bit or modified bit. It tells that if the block is modified or not. Right? Block is modified or written. Okay, written or not. Block is modified. Mainly it is written. Okay, because there is two operation only you can do, read and write. Right? There is no any other operation. Only two operation. Either you can read it or write it. So modified here means written. Right? So if the block is written or not. Okay. And one another bit, reference bit, it is mainly used for LIU representation, implementation, and maybe there can be another bits also. We don't care, but these are the more to like more to used bits. Okay, there may be many bits. Okay, I am not saying that only these three bits. There can be many bits, but that is not required. Okay, that is not required. Okay, so now we will see average memory access time, right? So So in the cache, okay, in the cache, what happens? Some PYQs, okay, some PYQs, okay, it's like majority, okay, majority PYQs from three mappings, okay. That's why I have spent too much time, right? Too much time in three mappings, like majority of PYQs, okay, majority. Then many other topics like average memory access time and so on, okay, and so on, different topics. Okay, now the next important thing we will see is average memory access time. Okay, this we will see, like here also some pyqs will be there, and that is also important. Okay, that is also important. So some pyqs, yes. And in and other some small topics, like we will see in further detail, in today's only we will see. So all this content rest of the pyqs, okay, rest of the pyqs. So this is the very important topic, right? Cache is the very important topic from PYQ's point of view. Now average memory access time. AMAT means average memory access time. Okay, average memory access time. So what it says, average time taken to access the memory considering both hit and misses. Okay, because sometimes data is in cache so that you will get fast, and sometimes the data it is not, so that's why it is slow, right? So that's why we are more concerned about average time. What is the average time taken? What is the average time taken to access the memory, right? To access the memory, considering both hit and misses. Okay, considering both hit and misses. Now, before that, look into this multi-level caches. So inside, if you look into your processors, okay, if you look into your processor, so modern processor uses multiple level of caches. Okay, multiple level of caches. So this is the multi-level, like CPU CPU, then L1 cache, L2 cache, L3 cache, okay, and main memory cache. So L1 cache is fastest, then fast, then less fast, and slow. And size, if you see, then it is smaller, okay, smaller. Then it is small, then it is big, okay. So this is the size wise, okay. This is the size. Now multiple levels of caches you will find if you look into the processors, right? If you open your processors, then this way some level of caches is been there, okay, level of caches. See why if someone can tell why the multiple level is required, someone can tell why. Can someone tell why it is required? Yeah. So see what the CPU required. CPU required mainly two things, right? So see what is the, okay, what is the why we are using the cache? Okay, we are using the cache for two main reason, right? Two main reason. First thing is we don't go to main memory, right? We don't go to main memory, so that's why we are storing it. So first reason is that size, right? Size is the issue, right? What is the issue? Okay, what is the issue? Maybe I can tell what is the issue for cache. Right? Issue for cache. So first thing is size, right? Because it is costly also, it is costly, right? And what is the second thing? See, we want things to be faster, right? Assume that if you assume that you have typed www dot assume that leadcode.com, okay, lead code. Assume that you have typed lead code, but if lead code have been slow, right? You don't have interest, right? You don't got interest because our human tendency is like that. We want everything faster, right? We want everything faster. So second issue is speed, okay, speed, right? So first is size and speed. So how you can manage two things, right? How you can manage two things? Because you can't increase the size. See, you can't increase the size because the cache is costly. If you check Amazon after the lecture, okay, you check the price for the cache and main memory, you will find that size of cache is very much, okay. Cache is very much. And if you go into the levels of hierarchy, right, we have seen if you go into the levels of hierarchy, your slowness, like you will get the slow, right? You will get the thing slow. Here it is mainly faster than it is, here it is fast, and here you will get the slow, right? So if you increase the hardware also, right, if you increase the size also, you won't get that much good speed. Yes or no? You won't get that much good speed. Yes or no? Tell me yes or no. You won't get that much good speed. So we have to balance two things, right? We have to balance size also, we have to balance speed also. So that's why what we have done, what the engineers have, what not we not we but engineers, okay, not we but engineers. So engineers have decided that why don't we put into the levels, right? So here it is small, right? So here you will get very much fast. Then level 2 somewhat bigger than L1, but it is fast, right? It is fast, somewhat slow than L1, but it is fast. Then it is less fast, right? Less fast, then less fast, and so on, okay. So if you do this thing averagely, okay, averagely, you will get the two benefits, okay. You will get two benefits: size also and speed also. Got it got it got it Average, okay. That's why we are concerned about average. So average, okay, averagely we get the things fast also. And see, we get the things fast also. And because because in the levels, okay, in the L1, L2, and L3, this is big, this is small, and this is smaller. So this is small, then this is little big, this is little big. So many things we can store in this hierarchy, right? Many things we can store in this hierarchy. So we got the advantage of both the worlds, both, like size and speed. Got it got it this thing. That's why the engineers have thought of this way, okay, multi-level caches. Yes. Okay. Now we will see this. We will see next topic. Okay. We will see next topic. So there is something called as unified versus split cache. So your L1 cache will be split into two. Okay. So your L1 cache is split. Okay. It is also called as split cache, and this L2 and L3 is also called as unified cache. Okay. So why? Because L1 is used for two. Okay. D cache, which is for data. Okay, and I cache. Okay, which is for instruction. So data cache, it stores the program data. Right? It stores the program data, which is operands, variables, and so on. Okay, and instruction cache, it stores the instruction. Okay, it stores the program instruction. So your L1 cache is split into two. Right, if this is the L1 cache, it is split. Okay, so it is D cache, and this is your I cache. Okay, it is split into two, and your L2 and L3 will be your unified cache. Okay, so it holds the data and instruction together. Got it? It holds the data and instruction together. Yes. Now see this another point, important point. So CPU doesn't know explicitly about existence of cache. Okay, so I told you earlier that we will look into this thing. So CPU doesn't know explicitly about existence of cache. Okay, what the CPU will do, it issues the read or write request using the address of main memory, right? Address of main memory. Now now it just access, right? It just access. Now CPU doesn't request like cache request or main memory request, right? Like CPU doesn't do like it is a cache request, it is a main memory request. What it does, it only generates the CPU always issues the main memory request, right? Main memory request, and the cache logic will decide how it will be served, right? How it will be served, because CPU have asked, CPU have requested something, right? So that we have to serve now, yes or no? CPU have requested something, so we have to serve. So our cache logic will decide how it will be served, right? How it will be served. So entire memory hierarchy appear to processor has single unit, right? Single unit. Like if you have, so for example, see if this is the CPU, and if this is the L1, this is the L2, this is the L3, and this is the main memory, right? So CPU have generated the main memory request. So this entire thing will be as one unit, right? One single unit. Yes, CPU, got it. So this entire memory hierarchy appear to processor has single memory unit. Okay, and CPU doesn't know about the existence of cache. Okay, existence of cache. Right? So this is some good short notes, right? Mainly that is for your better understanding. Okay, your for better understanding. That's not required for the gate PYQs, but I have put it just for the better understanding. Okay, you can remove also, you can put also. It's up to you. Okay, it's up to you. Now we will see. We will see the main thing. We will see the main thing. What is hit? What is miss? What is hit time, miss penalty, and everything. Okay. So now, okay. So what is hit? What is hit? When when CPU uh, accessed. Okay. CPU when CPU requested when CPU requested when CPU requested thing is present in cache, right? Is present in cache. Yes or no? So that's why it is called as hit. Okay. And what is miss? When CPU requested thing is not present. Okay. Is not present in cache. Okay. Is not present in cache. Then it is miss. Okay. When it is, then it is miss. Now, now see, Now see, the time seen by CPU when the cache hit occurs, okay? When the cache happens, see, when the cache hit happens, okay? Cache hit happens, whatever time which is seen by the CPU, that is when item is in cache, okay? When item is in cache, so that is cache hit basically. So total delay or time or latency seen by the CPU to access it, okay? So what is the total time? Okay, what is the total time which is seen by the CPU? Like when the heat happens, okay, so what is the total time which is seen by the CPU? That is called as hit time. Okay, that is called as hit time. Okay, and the cache hit time, which is same as cache memory access time. Okay. So if someone can ask that, hey, what is the cache access time? So tell them that it is same as cache hit access time. Okay, cache hit time. So a cache hit time and cache memory access time. Okay. So access time means you are accessing, right? You are accessing something. So access time and hit time is same. Okay. Access time and hit time is same. Now, now see this picture. Now see this picture. Okay. Now see this picture. Okay. Okay. So first thing is, what is the miss penalty? What is the miss penalty? Okay. Now we'll see about something related to miss. Okay. The time required to fetch. Okay. Hierarchy. Okay. From memory hierarchy from lower level. Okay. From lower level plus time to deliver this block to the processor. Okay. So the miss penalty will be time required to fetch the block. Okay. To fetch the block. See, if something is missed, right? If something is missed, because if the CPU requested data is not present, so that is miss. Yes, that is miss. If CPU have requested something, then it is miss. Then what happens? What happens? We have to serve now. We have to serve. So there is something called as miss penalty. What miss penalty will say that time required to fetch the block from memory hierarchy from lower level. Okay. So see, uh, yeah, maybe I can tell here only. So this is the lower level, right? This is the lower level, and this is the higher level. Okay. So CPU will first access L1, right? Now if this is the miss, right, here if it is miss, what happens, it will ask to L1, it will ask to L2, sorry, it will ask to L2, right? Because in the L1 it is miss. Now if L2 have block, okay, if L2 have block, what will happen? It will give to L1, right? So this time is called as miss penalty time, right? So that's one only is required. So to fetch the block, right? To fetch the block from memory hierarchy from lower level. Got it? Plus, plus time to deliver this block to the processor. Okay, time to deliver this block to the processor. And once we have brought from lower hierarchy, okay, then we have to give, then we have to deliver also. So that time is called as your miss penalty. Got it or not? Yes or no? Okay, yes. Okay. Now, what is the miss time? What is the miss time? See, total time spent processing the miss. Okay, processing the miss, total time spent. So miss time will be miss penalty plus hit time, right? Miss penalty plus hit time. So miss penalty will bring the block and all. Miss penalty will bring and all. Plus what is the hit time, right? Plus what is the hit time? See in the see, have you got, tell me, first thing tell me, have you got whether it is a hit or miss? Have you got whether it is a hit or miss? You have accessed it, yes or no? You have accessed the case, then only you can get to know whether it is hit or miss. Yes, you have accessed it, then only you have, yeah, by checking the case, right? By checking the case. So, so that is, I have already written cache hit time is same as access time. So this particular term is your access time, right? Your access time. It's it is used for checking whether it is whether hit or miss, right? Whether it is hit or miss. Now you got a miss. Now you got a miss. So you have to solve it. You have to solve it. So what is the extra time, right? What is the total extra time? See here, I have already written. So time to fetch plus to deliver, right? To fetch it and plus to deliver this block to the processor. Okay, because we have to give now, right? Because CPU have requested something, so we must have to deliver it. We must have to deliver it, right? So this time is your miss penalty time. This total time is your miss penalty. So plus miss penalty. Yes or no? Yes or no? So plus miss penalty, right? So this is the time. The total time is called as miss time, right? Miss time. Miss time is same as miss penalty plus hit time. Yes. Okay. Yeah. Now, what is the okay? So if this is these are the terminologies, okay, these are the terminologies and basic context, okay, basic context I have given. Now we'll see in detail. Okay, so what is the basic average memory access formula? So this is the most important. Okay, average memory access formula will be okay hit time plus miss set into miss penalty, right? Hit time plus miss set into miss penalty. Yes or no? Yes or no? Yes or no? See for how first of all how we can okay maybe I can give so assume that you have one level okay one level of cache okay one level. So if this is the CPU, this is the cache, and this is the memory. So what you do, what is the average memory access time formula? So it will be heat into okay heat ratio. Okay, so there is something called as heat ratio and miss ratio, right? Uh, yeah, maybe I have not written, but heat ratio will be what is the heat ratio? Total number of hits. Okay, total number of hits divided by total access, right? Total access. And what will be the miss ratio? What will be the miss ratio? Miss ratio is same as 1 minus if hit ratio is H, okay? It is also called as hit rate, okay? It is also called as hit rate. So hit rate or hit ratio or H, it's same, right? It's all are same. So miss ratio will be 1 minus H, okay? 1 minus H. And what is the meaning? Total number of misses, okay? Total number of misses divided by total access, okay? Divided by total access. You can put in your short notes, okay? Maybe I have forgot those 2 3 points, okay? Now if this is the one level, what you can do, heat rate into heat time, right? Heat rate into heat time. First you access, right? First you access. So either you can get a hit or miss, right? Either you can get a hit or miss. So heat ratio, right? Heat ratio into so this much time you will get a hit into heat time, yes or no? This much time you will get a hit into heat time plus 1 minus h, right? This is your miss. This is your misses, right? So this much time, this much time is your misses, right? Into miss time, yes or no? Into miss time, yes or no? So this is the simple formula, right? Heat ratio into heat time plus miss ratio into miss time, right? Now miss time is have two terms, right? Miss penalty plus heat time, right? Miss time have two terms, miss penalty plus hit time. See here, right? Miss penalty plus hit time. See, yes. Now, what I can do? Can I take hit time common because hit time is present in both the terms? Can I take hit time common? So if you take hit time common, so now look this formula. Now you look this formula. Average memory access time will be hit time, which is common, plus miss rate. See, plus this is the miss rate, right? This is 1 minus h. This is miss rate into what it is left, miss penalty, right? Plus miss penalty. So that's only written, right? So this is the basic formula. See, any formula you can take, right? Any formula you can take. Any formula you can take. It's up to you. Like this simplified formula you can also take, and bigger formula also you can take, right? Now, yeah, miss for penalty definition that we have already seen. Okay. Now some now this important note. Okay, important note, which which everyone must know. So majority of resources, okay, majority of resources defines miss penalty as additional time required for an access in case of miss, not including time to check the cache hit. Okay, not including time to check cache. Okay, not including. See this clearly. Not including time to check whether it is hit or not. Right? Whether it is time to check the cache and what to check whether it is hit or miss. Okay, whether it is hit or miss. Okay, so majority of resources miss penalty won't include. So that's why what can be your miss time will be you have to explicitly add, right? You have to explicitly add hit time, right? Excess you have to explicitly. Got it? Got it? You have to explicitly add in this case. Okay, you have to explicitly add. Now, if in question explicitly they have mentioned that miss penalty, time to check the cache. Okay, miss penalty includes time to check the cache. Then your miss time is same as miss penalty. Okay, you don't have to include again. You don't have to include again. Okay, you don't have to include again. So these two things you have to take care. Okay, these two things you have to take care. Like what it is given in the question. If see if nothing is given in the question. Okay, if nothing is given in the question, you can go with this. Okay, because majority of resources follow it. So by default you can assume it. Okay, by default this is by default. Okay, you can assume it. But if it is explicitly given, then you have to use this. Okay, you have to use this. So there is one question. So it is parallel. So it is parallel means signal from CPU to cache and memory goes parallel. See, that's what I told. CPU won't give the signal parallelly, right? Because CPU doesn't know. CPU doesn't know that there is a cache or not. CPU doesn't know that there is a cache or not, right? It only requests. It only requests. It is up to the logic. So see, it is like the like parallelly things and all. It's based on the implementation, right? Like hierarchical access or parallel access, right? Parallel access or hierarchical access. It is those are the implementation things. Those are the implementation things. Means if in question, so there is one another question. Means if in question miss penalty directly given, then no need to add hit time. Uh, okay, if in question miss penalty, see if they haven't specified anything about. Okay, so there is two things. See, there is two things. First thing, if in question they have explicitly tell this miss penalty, okay, miss penalty. If they have given the miss penalty and they have explicitly mentioned also that it includes the time to check, then no need to include. Okay, then no need to include. Now, what you can do, based on the options. Okay, based on the options you can edit, and you can check whether you have to take or not, right? Because see, by default you can take it. By default you have to edit, but sometimes what happens that we can't, because there are many discussion involved in this type of questions in miss penalty, because some majority of resources follows it, majority of resource doesn't follow it. So you can always check the options and you can go it. Okay, you can you can check the options and go it. It won't take much time. Yeah, but by default you can assume this thing. But but explicitly if it is given, then you can go. Okay. Yeah. Now, what is the average memory access formula if two levels of cache is given? If two levels of cache, okay, if two levels of cache. So average memory access formula. So don't look this. Okay, don't look this currently. Look this. So if CPU, so now you have two levels. Okay, if you have two levels. So if this is the CPU, this is the L1, this is the L2, and main memory. Now see, assume that two levels, right? L1 and L2. Now CPU generates main memory request. What can happen? First, it will go to L1. So in L1, whether it will be a hit or it will be a miss, right? It will be a hit or it will be a miss. Now, if it is a hit, okay, if it is a hit, then L1 hit time or L1 access time, right? So that is denoted as TL1, okay, TL1. Now, Now, if it is a miss, okay, if it is a miss, in L1 you got a miss, okay, in L1 you got a miss, you go to L2, right? Now you go to L2. So again, two scenarios, L2 hit or L2 miss. Now if you go to L2, okay, you go to L2, then two terms you have to include. First is L2 access time, right? And first thing L2 access time, right? Because L2 hit you got, so L2 access time plus you have gone to L1, right? You have gone to L1, then only you have came to know now. Then only you have came to know that in L1 you got a miss, right? So you have to include that time also. Okay, you have to include that time also. So DM about to start. Okay, so yeah, it's like some, like till now we can do it, and we can proceed other things in the tomorrow's class. So they now in the L2, okay, in the L1 miss, you can go to L2. So L2 also you can get a hit or miss, okay. Now if you got L2 miss, okay, if you got L2 miss, so here also, if you got L2 miss, then you go to main memory. So T main memory, right? But you came to L1, you came to L2, then only you can get to know, right, whether it is hit or miss. So you have to include both, okay? You have to include both. Now just simple, right? Now just simple. See, now you just have to follow each and every path, okay? Each and every path you have to follow. If you follow this path, then L1 hitted into TL1, right? Plus L1 miss set, so L1 miss plus into L2 hit, okay, into L2 hit into TL1 plus TL2, okay, TL1 plus TL2 plus, right, plus L1 miss, L1 miss, and L2 miss. Okay, L1 miss and L2 miss into entire time at TL1 plus TL2 plus T main memory at this term. So every time, don't mug up anything. Every time, just make the diagram and go it. Okay, and go with it. Yeah, and if you simplify this equation, okay, if you simplify, so you will get this. Okay, you will get this. This is the simplified version. Okay, simplified version. Yeah, so this term I have written the what is L1, M1, T1, H1, and everything. Right now, one another thing is here. Okay, one now next point is here. If number of read and write instructions given, okay. So if number of read and write instructions are given and different hit and misses are given, right? For read and write, different misses are given, like some misses for read and some misses for write. So what you can do, how you can calculate the average memory access time. So percentage of read plus you have to explicitly find average memory access time for T read, right? Like for read plus percentage of how many writes, right? Percentage of how many writes into average memory access time for in case of write, okay? In case of write. So this way you have to find if number of read and write instructions are given and different hit and miss is given. Okay, different hit and miss is given. Yeah. So something if you want to you can go, but then you can watch the recording. Okay, maybe I can complete the cache today, and tomorrow we will see the next two topics, which is pipelining and all. Okay.